So good morning to all. So we are discussing different types of CROs. The previous lecture we are seeing the dual beam oscilloscope and dual trace oscilloscope. The block diagram representation of dual beam CRO and dual trace CRO. So if you consider the dual beam CRO, so the name itself says that it is having two electron beams. It produces two electron beams and it is having two vertical amplifier sections and two vertical deflection plates having one horizontal deflection system. So whereas coming to dual trace oscilloscope, so tracing of the two signals, signal 1 and signal 2, or signal A and signal B. Okay, so like this, it will traces the number of signals, whereas dual trace oscilloscope, it traces the two input signals by using a chopping electronic switch. So with that frequency, it will be, so with the frequency generated by the switching circuit, so it will connect the two signals for a given period of time. So with respect to sweep generation. Okay, and in other in the alternate mode, it will be selects the two signals with respect to the sweeping voltage. Okay, and in other mode, chopping mode, so irrespective of the sweep voltage, sweep rate, so it will be selects the each signals. Okay, and that selection of the different signals is applied to the vertical amplifier and to the vertical deflection plates. So like that, so the dual trace oscilloscope will be traces the two signals with a single vertical amplifier, whereas dual beam oscilloscope will be dual beam oscilloscope uses the two separate electron beams. Electron gun is two electron guns, two vertical deflection plates, and one horizontal deflection plates will be used. So at a time we can represent one signal only. Okay, so like that, the dual beam oscilloscope will produces two beams of two electron beams, whereas dual trace oscilloscope will traces the two signals at a time. Okay, so like that we can produce the number of traces of the signals by using multi-trace oscilloscope. So if you can use eight signals at a time. You can produce the 8 signals at a time. Then we can use the multi-trace oscilloscope. Okay, and those are useful in the application of biomedical application. So to identify the signals of the voltages which are produced from different patients. The heart rate. Suppose we have to measure the waveform of ECE waveform should be analyzed for different patients. So at a time. So one signal is from one patient, another signal is from second patient. Like that, 8 signals should be connected to the 8 inputs of the CRO. Whereas this chopping circuit or switching circuit will select each signal for a given period of time, and it will be represented on the CRT screen. So like this, we can also use the multi-trace oscilloscope. Okay, multi-trace oscilloscope. Multi-trace oscilloscope. So and today we will see the sampling and storage oscilloscopes. So sampling oscilloscope and storage oscilloscope. So coming to today's concept, sampling and storage oscilloscope. These two oscilloscopes works on based upon the first the high frequency signals will be measured. So the sampling oscilloscope is used for the analyzing the very high frequency signals, whereas the storage oscilloscope is used for analyzing the very low frequency signals. Okay, so we will see each one. So coming to sampling oscilloscope, it is used for very high frequency signals. So generally, ordinary oscilloscope is having a bandwidth of 100 megahertz. So general oscilloscope or ordinary uh, sampling oscilloscope is having a bandwidth of the 100 megahertz. The high frequency can be improved by means of sampling the input waveform and reconstructing its shape from the sample. So high frequency signals can be first of all you have to make convert into the sample signals, and those sample signals will be reconstructed. Okay, so like that we can measure we can analyze the high frequency signals. So here the signal is to be observed is first sample, and after a new cycles the sampling point is advanced and another sample is taken. Okay, the shape of the waveform is reconstructed by joining the simple levels together. So sample levels together. Okay, so first of all we have to convert that applied input signal into the form of the samples. Okay, and from that samples will be reconstructed by joining the sample levels together. Okay, the sampling frequency may be as low as 1/10 of the input signal frequency. So we will consider the uh, sampling frequency, so which is used to uh, uh, collect the samples of the input signal. We can use 1/10 of the input signal frequency. Okay, if the input signal frequency is 100 megahertz, assume that the bandwidth of CRO vertical amplifier can be as 10 megahertz. Okay, so as many as 1000 samples are used to reconstruct the original waveform. So we are using 1000 samples are used to reconstruct the original waveform. So like that we can produce the. So this is the. So this is the block diagram representation of a sampling oscilloscope. So here, in addition to all the different vertical deflection plates in the CRT, so in the vertical section and horizontal section, we have some additional circuitry will be there. Additional circuitry will be there. So that is so the first one is sampling gate. So this sampling gate will be opens and closes by applying the sampling pulse. By application of the sampling pulse, this sampling gate will be opens and closes. When this sampling gate will open, the applied input signal is sent to the vertical amplifier. When the sampling gate is opened, it means it is on. So just we are saying that it is open, so it is just on. So when the sampling gate is on, it will produce the high voltage. Then the input signal which is applied to sampling gate is connected to vertical amplifier. When the sampling gate is off, the signal is disconnected to the vertical amplifier. Okay, this sampling gate opening and closing is decided by the sampling pulse. This sampling pulse. How this sampling pulse is generated? So is nothing but from the voltage comparator. So here the voltage comparator will compares the two signals. One signal is coming from ramp generator, and another signal is coming from the staircase generator. So staircase generator is nothing but the steps of the building. We can say it is the steps of the building. So how the steps having a building. So one over the other. So after that, okay, steps of the building. You can know that. Okay. So based upon the staircase staircase signals, staircase pulses will be generated by the staircase generator. Okay, and those signals is applied to the voltage comparator. Okay, and similarly, the another voltage signal from the ramp generator is applied to the voltage comparator. So the ramp generator is generated from the blocking oscillator. So for the blocking oscillator, we'll apply the trigger input. By applying the trigger input to the blocking oscillator, it will produces the oscillator signals, and those oscillator signals will be converted into ramp signals. So here we will use the ramp generator. So the oscillator signals will be, it may be sinusoidal signals, maybe that sinusoidal signals will be converted to the ramp signal, ramp voltage, linearly increasing. Ramp signal is nothing but it is increasing linearly. Okay, that linearly increasing signal is applied to voltage comparator, and at the same time the staircase generator is also applied. Okay, so when these two signals are equal, it produces a pulse. Voltage comparator will produce a pulse. That voltage pulse will be applied to sampling gate, and application of sampling pulse, the sampling gate will be opens. It means it will produces the on pulse. Okay, and when it produces the on pulse, the input signal is connected to vertical amplifier. So that will be given to the vertical deflection plates. Okay, so when these two signals, staircase generator signal and the ramp generator signal, both are equal, it produces sampling pulse. Okay, so at the same time, so it produces another higher case, higher step. So next staircase will be generated. Next staircase will be generated. Next step of the step will be increases. Okay, so I will show in diagram how this will be generates. Okay, so then what happens? The next staircase signal voltage is more than the previous staircase signal. So that next stage will be applied to the voltage comparator. Again, the ramp signal is generated. So, and again these two signals will be compared. When the ramp generator signal voltage and the staircase generator voltage are equal, again it will produce a sampling pulse. So when these two signals are equal, it produces next staircase signal. Like that, it will see. I will show you. Okay, these are the staircase generator output. So this is the form of the staircase generator, output of the staircase generator. So assume that initially the ramp signal is producing. Ramp signal is producing a signal. Okay, so when these two signals are equal, suppose at this point of the time, these two signals are equal, it produces a sampling pulse. And that sampling pulse is applied to sampling gate, and sampling gate is on, and input signal is collected. So again at that point the sampling pulse is collected. Okay, and again the next staircase will be generated, and again this ramp signal will be increased at that level of the voltage, and again it will be produces a sampling pulse. So like this it will be generates the number of number of pulses based upon the comparison of the staircase generator and the ramp generator voltage. Okay. So what are maybe the changes which are applied for the staircase generator? So that changes of the voltage is applied to the horizontal generator, horizontal signal, which is applied to the horizontal reflection plates. Okay. So this is the same as we are seeing same block diagram. Okay. That is the block diagram of the sampling oscilloscope. So I will show the diagram. waveform diagram, you can easily understand. See here. So this is the input waveform. Assume that this is the input waveform is changing in this manner. Okay. So here this is the trigger pulse. This one is the trigger pulse is applied. Trigger pulses are applied. Okay. So when the trigger pulse is applied, these sampling pulses will be produced. Okay, trigger pulses are applied, and thus that signal trigger pulses is applied to the oscillator, and from that oscillator it will be sent to the this ramp signal generator or ramp generator, and that ramp generator will produces. Okay, so the ramp signal is produces the ramp signal. Okay, so here consider here the ramp signal is generated here, and this is the staircase generator voltage. This is the staircase generator voltage. So here you can observe that. So this is the staircase generator voltage. This is a staircase generator voltage. You assume that this is the first step of the staircase generated voltage. Okay, so after this one is the staircase generator, and this is the ramp signal we are producing. The ramp signal is producing in this manner. Okay, so this is the ramp signal. It means the ramp signal is increasing. When the ramp signal is increasing and reaches the value of the staircase input voltage, and these two will be equal. When these two signals are equal, the comparator will be produces the voltage comparator will produces a pulse, and that pulse as a form as a sampling pulse. Okay, this is the sampling pulse. This is the sampling pulse is produced at the ramp signal and the staircase signals. Both are equal at that moment. At that moment, the voltage comparator will produce as a sampling pulse. When the sampling pulse is applied to a sampling gate, the input signal is at that point of input signal. Suppose at this sampling pulse is applied, so the input of the applied signal is at this point of voltage. That particular value of voltage is allowed to vertical amplifier. Okay, vertical amplifier will be senses this value of the voltage, and that is applied to the vertical deflection plates. Okay, so the next case what happens? So in the next case, the ramp signal is continuously produces and again discharges. Again in the next see here, once the first staircase voltage and the ramp signal both are equal, the staircase generator will produce as the next staircase signal. So this is the next staircase signal. Okay, so this is the first staircase signal. Okay, and this is the next staircase signal. Okay, so this is the second staircase signal. So again the ramp signal is producing here. From here the next ramp signal is producing, and again the ramp signal and the second staircase signals both will be compared here, and when these two signals are equal, the voltage comparator will produce as a pulse, so it becomes as a sampling pulse, and at that moment the sampling gate will be opens, and due to that, at that moment of the voltage which is presented as an input, that will be sent to the vertical amplifier, and when the second staircase voltage and the sampling ramp input both are equal, the staircase generator will produce as the next staircase voltage. It will produce as the next staircase voltage, and again the next staircase voltage is going to having as the like a step voltage. Okay, so it will be having a constant value at that particular level of the voltage. And in the next coming uh, sawtooth waveform or linear waveform, ramp signal. Okay, again this ramp signal will be generated, and the third staircase signal and the ramp signal will be compared, and when these two signals are equal, it produces the next ramp signal. So it may be assume that it is a fourth ramp signal. Okay, so when these two signals are equal, the comparator voltage comparator will produce as a voltage signal, pulse signal, sampling pulse signal. That pulse signal will make the sampling gate should be open or high, and at that moment of the input voltage which is present, so that voltage will be collects and it will sends to vertical amplifier. Like that, depending upon the comparison of staircase and the ramp signal, so the sampling pulses will be generated, and depending upon these applied sampling pulses, the input waveform will be collected as a form of the samples, collected as a form of the samples. So at this point, we will get only this particular time of pulse period, pulse time. We have this voltage. Suppose this is the another staircase input. So like that, we will get the number of samples of the input signal. We will get the number of samples of the input signals. Okay. So I think you are understand this concept, how these samples are generated for the given input by using a ramp signal or ramp signal and a staircase generator. So I think you are understand. So if you have any doubts regarding this, you can put a chart. If you want one more explanation, because these are important, so you may expect in examination will get these questions, sampling oscilloscope and storage oscilloscope. Definitely they will ask. So don't draw anything. If you have any doubts, we can put in the chart box. You can put. So I want one more explanation or something. If no doubts, you can put no. Okay, sir. No doubts like that. You can put in chart. You can use that chart. Okay. So this is also a figure which represents how the trigger pulses and sampling pulses will be generated. So when the trigger pulses are applied, these are the trigger pulses and these are the sampling pulses. Okay. So when the sample pulses are generated, the input waveform will be selected at that point of sampling pulse, and will get some shape of the waveform, and in the construction area, so we will get this type of the representation of the signal. So when we construct the waveform, we will get like this. So while we combine these samples, so we will reconstruct the signals. Okay. So this is the uh, real-time ramp horizontal reflection. Okay. So you can observe here. You can observe here the variation of the step changes, staircase voltage generation. Okay, so at that moment of the ramp signal is generating, so at this point of the equal point, so it will produce as the sampling pulse. When this sampling pulse is generated, it will recognize the input voltage. Okay, so like that we can produce the samples from the input signal, and those signals will be sent to vertical amplifier, and from that vertical amplifier we will apply to the vertical deflection plates. How much voltages we are applied, according to that the deflection of the vertical deflection plates, and this is the input signal which is applied to the horizontal deflection plates, and by combining that we can get the actual waveform. So reconstruction of this samples will be forms like this. So like this we can use the sampling oscilloscope. So here the input waveform is applied to sampling gate of the sampling oscilloscope. Okay, so input waveform is sampled whenever a sampling pulse opens the sampling gate. So input waveform is sampled whenever a sampling pulse opens the sampling gate. The sampling must be synchronized with the input signal frequency. So that sampling should be synchronized with the input signal frequency. It should be synchronized with the applied input signal and the sampling. Both should be synchronized. Okay. So signal is delayed by the vertical amplifier, allowing the horizontal sweep to be initiated by the input signal. So the signal which is applied for the vertical amplifier should be delayed. So before it should be applied to the vertical deflection plates, that signal should be delayed, because there is some time will be taken for the horizontal sweep voltage to initiate the input signal. Okay, these are the waveforms, how the samples are generated. This is also same as that one, and in the right side we are showing the reconstruction of these sample signals as a form of the samples, so we can get the signal. So this is the same we are discussing. So at the beginning of the sampling cycle, the trigger pulse activates the oscillator. So first one, the trigger pulse activates the oscillator, and it will produce as the linear ramp voltage. Okay, and the ramp voltage is applied to the voltage comparator, which compares the ramp voltage and a staircase generator. So when these two signals are equal amplitude, the staircase advances one step. When these two signals are equal, the staircase will generate the next staircase signal. Okay, and next staircase signal, and due to that, and when these two are equal, so it will produce as a sampling pulse, and that sampling pulse will open the sampling gate for the sampling of the input voltage. The resolution of the final image depends upon the size of the steps of the staircase generator. So how the final image will be obtained? So that will depends upon the size of the steps of staircase generator. So how many steps, small size steps or very large size steps? Okay. So if the step size is very low, so in such situation we can get a very closer representation of the input signal. So if the staircase signal is very high, the amplitudes of staircase signals is very high, then we cannot sample continuously. So there is a large distance will be there between the one sample to another sample. Okay, and due to that we cannot construct the proper shape of the input waveform. So that is explained here. So the smaller size, the smaller the size of the steps, the larger the number of samples. If the size of this staircase steps is very small, so then we can collect the number of samples, larger number of samples, and higher. Okay, if the higher we can we cannot get proper way. I mean, we cannot get the if the step size is very high, then so we will get the small number of samples. Small number of samples. So the while the reconstruction, so it will looks like a dot here, another dot is somewhere like that. So when the this step size is very low, so we will get the large number of samples, one after the another, very small distance. So with that representation of small dots one after the other, we will get the proper representation of the waveform. So with that we can get the higher resolution. Okay. So the next one is so storage oscilloscope. So the next one is a storage oscilloscope. So here storage of this uh, so storage is nothing but so storing of the waveform. So here we are applying certain waveform signals. So the applied waveform signal is should be stored. How we can store that applied signal? Okay, so because the applied signals are applying to the deflection plates. Based upon the application of this voltage, the electron beam which is produced from the electrodes cathode, these electrons will move through this deflection plates and it will falls on the phosphorus screen. When this beam of electrons will fall on the phosphorus screen, a short period of time it will be visible. After that it will be disappears. When the beam of electrons or the electrons will be travel through the deflection plates, okay, and those beam of electrons will be bombarded with the phosphor screen, the phosphor material which is coated on the screen of the CRT inside. Okay, so when these electrons will be strikes to the this phosphor material, so at that point of striking, so there is a illuminance of the light will be occurs. So after certain period of time, so it may be in terms of seconds, within seconds or few seconds, that incidence, after the incidence, that illuminance will be disappears. So we cannot store, or otherwise we cannot also observe continuously. So the beam of light will disappears. Okay, the light which is generated at the phosphor screen will disappears. So if the signal is continuously falling on that particular area, then only we can observe. So suppose the signal is just increased and decreased. Suppose the signal is non-periodic signal. Non-periodic signal. If the periodic signal is there, same frequency and amplitude, so we can produce the output. So we can observe on the screen. If the signal is periodic nature, that periodic signal is directly applied. That periodic signal is applied. Exact. So when the beam of electrons will be falls on the phosphor screen of the CRT, so the light will be illuminated. Okay, and that illuminated light will not present continuously. So after a few seconds, the light of beam will be disappears. So storage of such signals is difficult. Okay, so before that we will see that is persistence. So what is the meaning of persistence? The ability of the trace to remain visible on the face of the CRT. So the ability of the trace to remain visible. So how much time we can visible the trace of the signal on the CRT screen. So that is a persistence. So how much time it will be provide the signal. Okay. So that depends upon the type of the phosphor material or phosphor coating which are used in the inside of the CRT. So in the inside of CRT we will coat the phosphor material. So the type of the phosphor material we are coated. So based upon that the persistence duration was changes from micros few milliseconds to the seconds. Okay, but by using the storage oscilloscope, this persistence level should be increased to nearly hours. From seconds to the we can increase the hours also we can present. So the persistence levels will be increases. Okay, so that we will see in the next class how we can increase the persistence level. So how we can store the applied signal. So what are the main components present in the storage oscilloscope? Okay, so if you have any doubts you can put a chart. So in the chat box you can put your doubts or something, or you can ask any doubts.